welcome back to my channel. Today we are going to learn neighboring group participation, which is called NGP in organic reaction mechanism. We have already covered SN1 and SN2 single prime mechanism for allylic rearrangement reactions and SNI, that is nucleophilic substitution internal mechanism. And this is one of the most important mechanism so far because it increases 1,000 times rate of reaction as compared to nucleophilic substitution SN1 and SN2 mechanism. Like it, share it, and give comments to this video and solve more problems. So let's start. NGP. What is NGP first? We will see. So what are the parameters you should have to have NGP in a molecule? So as the definition says, a nucleophilic group with an unshared pair of electrons beta to the leaving group. So basically you should have this kind of structure where two carbons are there and one carbon is having the leaving group. The neighboring carbon is having a nucleophilic group having a lone pair of shared electrons. Okay, so which participate to push this leaving group out of this molecule. Okay, like neighboring group says neighbor until your neighbor push to you, like you start working for it. Same way this Z, which is a nucleophilic group, will push this leaving group and form a cyclic intermediate. So what is the mechanism? Since this nucleophilic group is pushing this leaving group from the back side, so backside attack is happening, that is SN2 mechanism. The mechanism is rate of reaction is slow, and you can notice inversion happens when you have SN2 mechanism. So cyclic intermediate. Now in this you have again two possibilities. The nucleophile which is going to enter, either it can enter from this carbon. Since it is showing symmetrical, it can enter from either of the side and open the ring, right? Which is again a backside attack. So it is SN2 mechanism again, which causes inversion. So inversion creates a retention of configuration. So again, as you notice, from the starting material is having Z and L anti to each other. Same way in the output, you have Z and nucleophilic group anti to each other with the retention of configuration. So 2 inversion creates a retention. And that's what's the definition. So this Z group participate temporarily and control the rate of reaction and stereochemistry of the reaction. So normally if you have SN2 mechanism, that gives you the inversion of the configuration, while here in NGP you get the retention of configuration. So what is the importance of this NGP? The rate of reaction 1,000 times faster than the normal substitution mechanism. So we also call it enchimeric assistance. And you have the configuration of a chiral which is retained, or you will get the racemized product, but you will not get here inverted configuration. So it's easy to identify, and we will see by solving the problems how this NGP works. Okay, so let's start. Let's say you have a problem called like active 303-bromo-2-butanol, which you are treating on with HPR, gives you the racemic dibromobutane. So we have to justify it. So for that you should know how to draw the 303-bromo-2-butanol. Okay, so for butanol means it is having the 4 carbon chain, and 1 2 3 4, you can see 4 carbon are there, and 3 position you have a bromine, and at 2 position you have a OH group. Butanol, all is for OH group, right? And we have drawn the Sauer's projection where you are showing the two groups are anti to each other. Okay, so you have to draw a conformation in which you are showing it anti to each other, and they are asking you to draw trio conformation. And trio conformation, as you can notice here in this Sauer's conformation, the 2H group and 2Me group are on the same side. Okay, so 3-bromo-2-butanol, and the condition is giving in the acidic condition. And we know what happens once you have acid. The lone pair present on the oxygen will take this proton and creates a good leaving group as compared to OH. Okay, so as compared to OH, OH2 plus is a better leaving group. And you can notice for NGP, the criteria is with respect to the leaving group on the beta carbon, you should have a lone pair bearing group. and we have here bromine, right? So this bromine will donates its electron to this carbon and help to release this OH2 from here and forms a cyclic intermediate. So this is the backside attack. So it is the SN2 mechanism with the loss of water. And you have a cyclic intermediate bromonium ion, right? And you have Br minus left here, which is acting as a nucleophile. So this Br minus can enter either from the A pathway or it can enter from the B pathway. Okay, so two possibilities are there to attack for this Br minus from the back side, which is the SN2 mechanism, right? So let's say if you follow the A path, okay, so this side it will open the ring. So Br is coming on the original position. So you can see for A path, Br is here, and this Br minus nucleophile is attacking from the down. So the HME is going above the plane. So this is one of the confirmation, and the other one is, you can notice, if it follows a B path, so bromine is attacking from here and HME is going above the plane. So opening of this ring, Br is going on the other carbon, and you have this. So if you notice the two and see, the two are the enantiomer of each other, and therefore we call it plus and minus isomer. It is the racemic mixture of two and should be optically inactive, right? Racemic mixtures are optically inactive. So active 3O is giving you the optically inactive product with NGP here, and the rate of reaction is of course 1000 times faster as compared to normal SN1 and SN2 mechanism or SN2. Okay, so the formation of this, which is optically inactive, can be explained by NGP involving the bromine only. If you have only SN2 mechanism, then you will have the inverted configuration, right? You will have only one enantiomer, which is inverted configuration. So we can prove that the mechanism has gone through with NGP. Okay, the next is on acetolysis, racemic 3O, 3-phenyl 2-butyl tosylate gives racemic 3O. So they have given the acetate, right? Instead of tosylate, you are creating the acetate here, while racemic erythro isomer gives racemic erythro 3 with retained configuration. Okay, so it's a quite big structure. First of all, we will see that how to draw this structure. 3-phenyl 2-butyl tosylate. Butyl means 4 carbon chain, right? So again we are writing it in a sawhorse conformation, and you can say 3-phenyl. So with respect to this, 1 2 3, at third carbon you have a phenyl ring, at 2 position 2 carbon you have a tosylate group, OTS, and the two are anti to each other. We have to draw a conformation in a way, because this is a condition for NGP. Okay, so the leaving group and the neighboring group should be anti to each other so that it can participate its electron from the back side. 3O. 3O again same as I told you, the two same side groups are on the same side here, methyl methyl and hydrogen hydrogen. So this is the 3O conformation of 3O3-phenyl butyl tosylate, right? So two possibility to draw it. Okay, one is this, the other is, you can see, you can write the 2-methyl on the closer to the phenyl ring and hydrogen closer to the tosylate, which is the leaving group. So plus minus 3O isomer, and in both the cases with SN2 of this pi electron. Okay, here the pi electron of the aromatic ring will be participating in the releasing of this OTS group. Okay, so this pi bond is giving its electron from the back side, SN2 attack, and releases this tosylate group, which is a better leaving group, and forms the phenonium ion as an intermediate. Okay, so two possible conformation you can see with respect to two enantiomers. And now since we are talking about acetolysis, so acetic acid, two possibility, as we have done in the first problem, either it will go attack from the A side or it may attack follow the B path, right? So in both the cases it forms two products. Okay, so this is called mesophenonium ion. Mesophenonium ion because the two symmetrical groups are on the same side, right? Methyl methyl and hydrogen hydrogen are on the same side. So again acetolysis, SN2 backside attack, two possibility will generate the two enantiomers plus minus. Same way follows A path. So AAC will come here. So one is, you can see with the retained configuration. So if it follows the B path, it is a retained configuration, while other you can say the rearranged configuration, right? Retained and rearranged, plus minus 3O, 3-phenyl 2-butyl acetate. Clear? So this is they are asking for the 3O isomer, and similarly they are asking for erythroisomer which generate the erythro one. So we will see that also. Before going to that, you can see one enantiomer is formed by NGP, as I told you, that is a retained configuration. Another is formed by rearrangement configuration. Now, erythroisomer. So you have to draw erythroisomer for same molecule. In that case, you can draw one methyl and one hydrogen on the same side. Okay, so in that case, the two methyl are trans to each other in this configuration. Similarly, with respect to phenyl ring, if you draw a hydrogen here and there with respect to tosylate methyl. So the two are enantiomer only, plus minus erythroisomer. As we know, the pi electron of the aromatic will participate as NGP, releases O to TS by SN2 mechanism, and you will get the inversion of configuration, and intermediate, that is cyclic intermediate, which is again the you can say clue for NGP. Cyclic intermediate, you get it in NGP only, right? So you are getting this, which is again called active phenonium ion, because here one methyl and one hydrogen is on the same side. Similarly, on the other side also one hydrogen and methyl present. So we call it active phenonium ion. Two possibility for acetolysis, same way, either path A or path B for both intermediate, and you have plus minus erythro 3-phenyl 2-butyl acetate. You can notice one is a compared to the starting material, one is a retained configuration, just you are replacing OTS with OAC, and the other one is the rearranged configuration, right? You can just notice rearranged. Similarly, for this you have one is retained, other is rearranged configuration. So this is for the erythroisomer, and very important question for especially MSc students and for competitive students, those who are appearing in competition. They may ask you the final output, and you should know which output you will get it by this particular isomer, right? Erythro and 3O. So some points to note down, like each enantiomer of erythroacetate same generate by NGP or by rearrangement. NGP means retained configuration, right? In mesophenonium ion, like if somebody asks you like what is the effect of rate of reaction, if you compare the 3O and erythroisomer, the rate of reaction is faster in which configuration? So in mesophenonium ion, like which was the case in the previous ion, the two methyl groups are cis, while here active phenonium ion, it is trans to each other. So basically this intermediate is thermodynamically more stable, right? So rate of reaction for erythroisomer should be faster than the 3O isomer, because this intermediate is thermodynamically more stable. I hope you understood this. Now, another problem where you have acetolysis of NT7 non-borononyl tosylate. So this is the structure is very much like 10 to the power 10 to the power 11 times faster than its saturated analog. So whenever this give you this clue about rate of reaction is 1000 times higher, 350 times higher, 10 to the power 11 times higher, it means the NGP is involved here, because such a huge rate of reaction you will get only by NGP. So now thing is, why this NGP, or how this NGP is happening in this structure 1 while it is not happening in structure 2. For that we need to see. As you can notice in this structure, you have a double bond, a pi bond in this ring, and a tosylate group which is a leaving group. Both are anti to each other, right? You have a double bond which is backside to this tosylate, and here also the pi bond electrons are participating to push this leaving group from the backside SN. Okay, one mechanism, because it is going to form a non-classical carbocation. Okay, so what is that? this electron is giving its pi bond is giving its electron to this bond, and it is releasing, creating a carbocation which is migrating between the 3 center, and 2 electrons are there. So non-classical carbocations are actually 1, 2, 3. 3 center, 2 pi, 2 electron, because 2 electrons are involved. So 3 center, 2 electrons are called non-classical carbocation. So this carbocation is not restricted to particular carbon, rather than it is delocalized carbocation, right? Non-classical, 3 center, 2 electron carbocation. And if the carbocation forms, we have the SN1 mechanism. Now for acetolysis, the acetolysis will happen from here, where the retention of configuration will occur, right? One possibility, it will occur from here, and this bond, it gives electron to generate back the double bond, right? So this bond is giving its electron, and you are having this structure, which is again the anti-7 non-bonded acetate with the retention of configuration. Okay, if it is SN2 mechanism, SN2 will push from the back side, you will get the inverted configuration. Rather, we are having here retention of configuration. And which reaction mechanism will be favorable, that we will see with respect to this rate of reaction only. The rate of reaction says it is 1000 times faster, means it is happening through NGP, which gives you the retention of configuration. So this is a statement which you can note it down, that retention of configuration gives strong evidence that C double bond C pi bond is acting as an effective neighboring group, which is enhancing the rate of reaction 10 to the power 11 times, right? Now what is happening in saturated analog? As it doesn't have the double bond here which can release this OTS, so here the normal SN2 mechanism will occur, where the OAC, the nucleophile, will attack here, and OTS is releasing via SN2 mechanism with the inversion of configuration. So the rate of reaction is very slow, and you are getting here. You can rectify this problem here. Oh, it's not OTS, it is OAC. Okay, so it's OAC because we are doing the acetolysis. So you have OAC here, okay, instead of TS, inversion of configuration. Retention of configuration is happening because of NGP. So the lone pair of electrons on heteroatom, the pi electrons participate in the NGP. Now this problem, where you don't have lone pair of electrons, you don't have pi bonds to participate, even though you are having here racemic mixture. If it is normal SN2, you should get only the inversion of configuration, right? But you are having here racemic mixture, which is again indicating that the NGP may be present here, and the rate of reaction is always, it is much higher as compared to usual substitution reaction. Now here what is happening? Now here you can notice OTS is a leaving group. Now with respect to that, we have to see how this NGP is happening. So basically, if you notice the C1 C6 bond, the sigma bond is participating, is giving its electron to release this OTS from this group, from this molecule. So basically the C1 C6 bond, sigma bond, is acting as a neighboring group to release this OTS, and it is creating a non-classical carbocation, a 3-center 2-electron carbocation, right? So SN1 mechanism, formation of non-classical carbocation. Now you have, since we know this positive charge is not restricted to any of the carbon, it is delocalized. So the acetic acid can attack either to this one carbon, or it can attack to this 2 carbon. Okay, so any possibility is there. In both the cases we'll get 2 products. So let's say if it attacks on the C1 carbon, you will have this structure, right? Acetolysis, you can also write it in the correct configuration, this one, where we are having the inverted configuration, right? Inverted configuration on the other side. If it attacks on the C2 carbon, here you will get the retention of configuration. Like if you compare the reactant and the product here, OTS is replaced with OAC. So retention of configuration. Fine. Retention of configuration, inverted of configuration. So here basically we are getting here the enantiomer, which are plus minus exo 2 norbornyl acetate. And this is possible, the recipe mixture is possible only because of the NGP, which is enhancing the rate of reaction as well. So lone pair of electrons, pi bond and sigma bond do participate as NGP. And this is going to be the last problem for NGP. Cis and trans 2-chlorocyclohexanol behave differently towards alkali. Explain. So we will see how does it behave. Cis and trans. So first of all, you should know how to draw that. 2-chlorocyclohexanol. Chair form cyclohexanol. You have a 6-membered ring in the chair form where you have OH group all, and at 2 position you have Cl, right? And first we are going to draw the trans isomer. Trans 2-chlorocyclohexanol means the two should be opposite to each other. EE, that is you have either axial position or equatorial position. So here the two OH and Cl are positions equatorially opposite to each other. So this is the stable trans configuration, right? Stable trans conformation, EE. But here we know if you are looking for the NGP, the two should be anti to each other. So we are just flipping this ring. In that way, you are just converting EE to AA conformation. Now OH and Cl is just opposite to each other. So this is a trans 2-chlorocyclohexanol, and we have the alkali. The base is present here, and we know what is the role of base, the abstraction of a proton. So if it abstract, this bond will give its electron to this. So you will generate a carbanion here, O minus. So O minus will act as a neighboring group then, right? Will give its electron to this and release the Cl part, right? Backside attack. Backside attack will be happening to release the Cl. So you'll be having the SN2 mechanism, and you have the cyclohexene oxide here. This OH minus is again abstracting proton. So this is how the trans 2-chlorocyclohexanol is giving you the oxide. Now the cis isomer, where the two are having on the same side, OH and Cl position are on the same side. So axial and equatorial. Either you can make Cl as equatorial, OH as axial, or OH as equatorial and Cl, both are cis isomer. Now, in the presence of base, same way, abstraction of a proton, O minus you will generate. But this O minus is not anti to Cl to attack the backside. So what is going to happen? So basically, it is going to generate a carbonyl bond, right? And this hydride shift will occur, followed by this hydride shift and release of this Cl. So basically, you are having here via SN2 mechanism only cyclohexanone, right? So you have a cyclohexanone here, hydride shift. In both the cases SN2, but differently you are getting the product. And this way you can explain how the cis and trans 2-chlorocyclohexanol behave differently. So this was our last problem, and you can solve now many problems related to NGP. There are plenty of problems in the textbooks. You can collect it from the Google and solve it. I hope you understood the concept of NGP. Very important topic for your CSIR net examination, which is you are going to have in January, right? And for those who are going to appear for GATE examination, for M.Sc. third semester student, they are having in their syllabus. So do practice it and solve many problems to clear your